As you can see behind me, progress on the project is moving quickly, and we are right on schedule.
I want you to imagine the pressure. $6.7 billion USD at stake, sitting directly in the path of the world's most violent wind speeds, exceeding 280 kilometers per hour. The goal was simple yet impossible. Create the world's longest asymmetric cable, stayed bridge to keep a 1,666-meter maritime artery open for 300,000-ton cargo ships. I will break down the process for you. First, we must address the asymmetry. Geography forced us to build a structure that is inherently off balance, a nightmare for physics. To prevent this dragon from snapping, I present to you the 2,060 megapascals ultra-high-strength steel. This is the strongest material ever used in global bridge engineering. The process starts here, in smart factories. Each main cable is forged from thousands of high-tensile wires, together exerting a force that could lift 10,000 aircraft. I need you to understand the scale of these cables. At 2,060 megapascals, they are designed to survive 120 years of relentless vibration and saltwater corrosion. Look at these robotic welding units. They work with a tolerance of less than 2 millimeters. In our world, a single millimeter of error means structural catastrophe. We fabricated these steel box girders in sections as large as football fields. I watched as they were loaded onto heavy lift vessels to begin their journey into the deep sea.
I'm here on the Thames, where preparations are underway to move this colossal structure through the heart of London.
Once on site, I deployed giant hydraulic strand jacks. These machines don't just lift, they fight gravity itself to hoist segments 270 meters into the sky. I must warn you about the wind at this altitude. It acts like a predator, capable of flipping these steel blocks. This is what we call vortex-induced vibration. To solve this, I designed world-first wind fairings. Look at these jet fighter wing shapes. They are engineered to split the wind and kill the lifting force instantly. Instead of fighting the storm, I make the bridge use it. The wind pressure now pushes the structure down, locking it firmly against our massive concrete foundations. But look beneath the surface. I drove 120-meter deep piles into the seabed, piercing through silt and rock to anchor this titan into the very bedrock of the earth. But the ocean is a slow killer. Saltwater is highly corrosive, designed to eat away steel and concrete over decades. To guarantee a 120-year lifespan, I implemented a sacrificial cathodic protection system on the underwater foundations. Look at this electrochemical grid. It forces the seawater to attack zinc anodes instead of our primary steel structure. Inside the pillars, every single rebar is coated with a specialized epoxy resin, creating an impenetrable barrier against chloride penetration. Above the surface, the concrete towers rise 270 meters. I utilized a continuous slip-form pouring method for absolute structural integrity. There are no cold joints. This is a single monolithic pillar of ultra-high-performance concrete, curing seamlessly in the humid air. Now, consider the threat of human error. The Lingding-Yang Channel sees over 4,000 vessels passing through every single day. What happens if a 300,000-ton cargo ship loses steering and rams directly into our foundation? I engineered a multi-layered crash protection system. Giant steel cofferdams surround the piers, acting as a massive crumple zone. Upon impact, kinetic energy is instantly absorbed and dissipated through these crushable steel cylinders, saving the main tower. The most stressful moment was the final closure, the golden joint. We had to connect the two massive bridge halves perfectly. Steel expands under the sun. Just 1 millimeter of thermal expansion during the day would make the connection physically impossible. I waited until exactly 3 a.m., when the ambient temperature dropped to its absolute lowest point, to lock the final bolts. Listen to the sheer mechanical force. Hydraulic wrenches torque the high-strength bolts precisely to their ultimate yield limit. The skeleton is now whole, but the true test is yet to come when the typhoon season fully unleashes its fury upon us. The typhoon arrives. A wall of black clouds and Category 17 winds slam directly into our creation. I am talking about 280 kilometers per hour, a force that easily uproots massive trees and shreds conventional buildings to pieces. Inside the command center, I am watching thousands of optical fiber sensors stream real-time stress data from the steel skeleton. Look at the wind fairings now. They are violently slicing through the air mass, successfully killing the aerodynamic lift. The vortex-induced vibration is entirely neutralized. The aerodynamic profile is forcing thousands of tons of atmospheric pressure downward. The 2,060 megapascal cables are howling in the wind. They are stretching and absorbing the kinetic shock waves flawlessly. The asymmetric towers take the absolute brunt of the lateral load. The ultra-high-performance concrete holds steady without a single microfracture. I designed this massive deck to sway up to 2 meters. This calculated flexibility is exactly what keeps the rigid steel from snapping. Below the churning surface, the 120-meter-deep piles are anchoring us to the planet's crust against extreme hydrodynamic drag. The storm breaks. The sun rises over the Lingding-Yang Strait. The Dragon remains completely untouched, but raw steel cannot handle heavy traffic. We must pave it. And I am not using ordinary asphalt for this Titan. I deployed a highly specialized epoxy resin asphalt. It must bond chemically with the steel plate and flex without cracking. Massive automated pavers deploy a perfect 5-centimeter layer of this black armor across the entire 6-kilometer deck. The paving temperature must be maintained precisely at 180 C. Any drop in heat will instantly destroy the chemical bond. Look at this pristine, flawless surface. The bridge is now structurally armored and ready to bear the weight of a regional economy. This bridge is not a static object. I designed it as a living machine equipped with a digital nervous system. We are installing thousands of miles of fiber optic cables along the steel guardrails to monitor every millimeter of structural flex. Look at the lighting array. Smart LED modules are tested to cut through the densest ocean fog, guiding heavy transport safely. But the Lingding-Yang Bridge is only half the story. The steel spans must connect to an underwater tunnel through a massive artificial island. I engineered this island using interlocking steel cylinders filled with dredged ocean sand to form an unbreakable fortress. Here is the portal, a massive concrete maw swallowing the highway and taking it deep beneath the seabed. Inside the tunnel, we mount gigantic ventilation fans. They are designed to purge toxic exhaust and smoke within seconds. I must ensure absolute fire safety. We test the high-pressure deluge systems, capable of drowning a vehicle fire instantly. All this data converges here in the central command matrix. An advanced AI constantly evaluates the structural integrity in real time. Before I open this artery, we conduct the ultimate load test. Dozens of heavy trucks drive across the asymmetric spans simultaneously. I watch the monitors closely. The steel deck flexes under the extreme weight, transferring the kinetic load perfectly to the main cables. The 2,060 megapascal wires hold firm. The deflection is exactly within the calculated millimeter limit. The physics hold. Final anti-corrosion coatings are sprayed onto the towering anchor points, sealing out the salt for the next century. Look at the scale of this achievement. We conquered the deepest waters, the deadliest storms, and the limits of material science.
This ambitious infrastructure project is currently on schedule, bringing new opportunities to the region.
The bridge is only half the battle. To cross the busiest shipping lane without blocking massive vessels, we had to go underwater. I present to you the world's widest steel shell concrete immersed tube tunnel. This is a completely different kind of monster. Building an underwater highway requires massive modular tubes, each weighing 80,000 tons. That is the weight of an aircraft carrier. We cannot build these under the ocean. They must be forged on land, inside a mega dry dock the size of a small city. Look at the steel shell construction. Automated robots weld thousands of steel plates to form the outer skin of the tube. Once the steel skeleton is complete, we pump self-compacting concrete into the hollow walls. No mechanical vibrations needed. This specialized concrete flows like lava, filling every tiny void to ensure absolute watertight integrity against the ocean's crushing pressure. When the tube is finished, we flood the dry dock. This 80,000-ton concrete and steel leviathan actually floats on water. Towing it out to the ocean is a high-risk operation. Specialized tugboats must drag this colossal mass through unpredictable currents. I had to calculate the exact hydrodynamic drag. One wrong maneuver, and the massive tube could capsize or break apart mid-ocean. We arrive at the sinking coordinate. The precision required here is agonizing. We have a tolerance of just 50 millimeters at the bottom of the sea. Water is slowly pumped into the internal ballast tanks. The massive tube begins its descent into the dark abyss. Sonar and acoustic sensors guide it down. The ocean floor is entirely blind. We are flying purely on digital instruments. At the seabed, a specialized gravel leveling ship has already prepared a perfectly flat foundation, smoothing out the ocean floor. The tube touches down, hydraulic jacks engage, pulling it tight against the previous section. The rubber seals compress, locking out the ocean forever. Once the tubes meet, we pump out the trapped water between the temporary bulkheads. This creates a vacuum. The crushing hydrostatic pressure of the ocean outside now acts as our greatest ally. Millions of gallons of water literally crush the two 80,000-ton segments together, compressing the Gina gasket permanently. I send the first team inside. Walking into a dry, hollow concrete cavern 40 meters below the ocean floor is an eerie experience. Heavy machinery cuts away the steel bulkheads, opening the artery section by section. Now, the interior outfitting begins. We lay down the exact same high-durability epoxy asphalt used on the bridge. But here, fire is a greater threat than water. I mandated a specialized fireproof silicate cladding across the entire ceiling. This material can withstand a 1,200-degree hydrocarbon fire for 2 hours without spalling or collapsing. The most terrifying phase is the final joint. We must drop a massive V-shaped wedge into a gap of less than 2 meters. At this depth, the water currents are violently unpredictable. Blindly lowering a 10,000-ton wedge requires sub-millimeter precision. I engage the hydraulic rams. They slowly push the wedge outward, locking the mechanical seals against the adjacent tubes. The final chamber is pumped dry. The pressure gauges stabilize. The seal is absolute. When the last steel plate is cut, workers from both sides finally meet. A cheer echoes through the concrete vault. Look up. There are 40 meters of ocean pressing down on our heads right now, yet not a single drop penetrates. The Lingding Bridge, the artificial islands, and the undersea tunnel are now physically united. The dragon is whole. The physical body is complete, but a giant without a brain is useless. I had to build a digital nervous system. This is the Intelligent Traffic Management System, a central AI that processes millions of data points every second. Inside the tunnel, I deployed automated inspection robots. They patrol the service galleries autonomously, searching for microscopic anomalies. Above ground, a network of millimeter-wave radars and high-definition cameras tracks the exact speed and trajectory of every single vehicle. If an accident occurs, the AI instantly redirects traffic, dispatches emergency drones, and adjusts the tunnel ventilation systems. We cannot afford a bottleneck. I installed massive multi-lane free-flow electronic toll collection gantries. These overhead scanners process thousands of vehicles per hour at highway speeds. You never have to stop. Before opening, I mandated one final, brutal quality control sweep. Laser profiling vehicles scan the entire 2-4-kilometer asphalt surface. We are looking for deviations no thicker than a single sheet of paper. The road must be absolutely flawless. At dusk, I initiate the total power-up sequence. Thousands of LED fixtures ignite simultaneously across the bridge and islands. Look at this glowing artery. It is not just a road. It is the ultimate engine for the Greater Bay Area. I need you to grasp the economic impact. We are cutting the travel time between Shenzhen and Zhongshan from 2 grueling hours to just 20 minutes. This eliminates the massive logistical detour around the Pearl River estuary, saving billions of dollars in freight costs annually. Fleets of autonomous electric trucks are already staging at the terminals, waiting for my final clearance to cross. Dawn breaks over the delta. The storm has passed. The mega project stands ready to breathe life into the global supply chain. I give the command. The electronic barriers lift. The toll indicators flash bright green. Thousands of vehicles surge onto the asphalt. The mega project is now officially alive and taking its first breath. I watch the structural sensors closely. The 2,060 megapascal cables flex dynamically, absorbing the kinetic energy of the moving convoy seamlessly. Down in the immersed tunnel, the massive ventilation fans roar to life. easily purging the exhaust of 1,000 combustion engines. The flow is flawless. There is no bottleneck, only a continuous river of steel, rubber, and cargo moving at highway speeds. This is not just infrastructure. I have built a 2-4-kilometer time machine for the global economy. We just collapsed the physical distance between two mega cities. A grueling 2-hour journey is now a 20-minute sprint. Look at the cargo ships passing beneath us. The 1,666-meter asymmetric span grants them absolute freedom of navigation. The Greater Bay Area is now a single, hyper-connected economic engine, ready to dominate the century. Nature threw its absolute worst at us. The corrosive salt, the Category 17 typhoons, the crushing oceanic pressure. But human engineering prevailed. We forged steel to conquer the sky and sank 80,000-ton concrete tubes to conquer the abyss. This bridge will stand here for the next 120 years, a permanent monument to the absolute limit of modern material science. I have shown you the anatomy of a Titan. You have seen the math, the metal, and the madness required to build it. The next time you cross a bridge, remember the extreme physics keeping you alive above the void.
As you can see behind me, progress on the project is moving quickly, and we are right on schedule.